Algebraic Structures, Lecture 4, Group Actions. Let us start with some motivation. Many basic examples of groups are given in terms of symmetries of certain geometric objects. For example, we define the dihedral groups as symmetries of irregular n-gons inscribed in a unit circle in the real plane. In general, one can very vaguely define the notion of a symmetry of some mathematical object as a bijective transformation of the enveloping space of that object, which leaves the object invariant. And all symmetries of an object form a group with respect to composition. And each element of that group transforms the object in some way. And so one can reformulate all this in terms of the action of this group on this object. And the aim for today is to introduce and discuss the corresponding notions. We start by definition of an action of a group on a set. So let G be a group and X a set. Definition: an action of G on X is a map which is usually written as dot, and it starts from the Cartesian product of the group G and X, and it goes to X. So to each pair, one element from G and one element from X, we associate one element from X. And this map is supposed to satisfy the following properties. First of all, E acting on X gives X for any X in our set. And the second property, if we act by A on the outcome of acting by B on the element X, this should be the same as acting by the product AB on the original element X. And this should hold for all A and B in G and for all X in our set. There are possible different notations. So A dot X can be sometimes denoted as A of X and sometimes simply as AX. So we act by a group element A on the element little x in our set X, and we produce an element from our set. So an element of a group acts on an element in a set and produces an element in our set. So this is our setup. Here are some examples. Example 1. Any group acts on any set trivially, in the sense that if we apply a group element to an element in the set, we get the same element from the set back. A dot X is equal to X for all A in G and all set elements little x. Example 2. Any group G acts on itself via left multiplication. So here we choose as X the set G, the underlying set of our group, and the action is left multiplication. Applying element A to an element X, we output their product AX. Let's check it. If we apply E to X, we will get EX, and this is of course X because E is the identity element for any X in G. Furthermore, if we apply A to the outcome of applying B to X, this will be ABX, and since multiplication is associative, we can put brackets the way we wish, so this is equal to AB times X, so the outcome of applying AB to the element X. And again, this is true for all A, B, and X. So this means that G acts on itself by left multiplication. Example 3. Any group G acts on itself by conjugation. If we take an element A in G and we apply it to the element X in our set X, which is our set G, so the outcome is the product A times X times A inverse. Indeed, let us check the axioms. E applied to X is equal to EXE, which is X, because E is the identity element. A applied to B applied to X is equal to A times B times X times B inverse times A inverse, and we can write it as AB times X times AB inverse. So this is AB applied to X. And again, this is true for all A, B, and X in our group G. So conjugation is indeed an action of our group on itself. Here are some further examples. For any set X, the symmetric group Sx on X acts on X by definition, because each element in the symmetric group is a bijective transformation of X. So we can take this element and apply it to an element in X, and we get as an output a new element in X. So by definition, S of X acts on X. Example 5. Let X be a geometric object and G the group of symmetries of this geometric object. Then of course G acts on X by definition, because each element in G is a certain transformation of the object X. Example 6, so that's a special case. We have the dihedral group D2 times n. This is a group of symmetries of the regular n-gon inscribed in a unit circle in R2. We can consider the set of vertices of this regular n-gon, and of course any symmetry sets a vertex to a vertex. So the dihedral group D2 times n acts on the set of vertices of this regular n-gon. Similarly, it also acts on the set of edges of this regular n-gon. Another example, by definition, the general linear group on a vector space V acts on this vector space V, because any element of this group is a bijective map from V to itself. It's a bijective linear map, but in particular it's just a bijective map, and the product is the composition. So we have the defining action of GLV on V. Here's a more non-trivial example. The group Z of all integers with respect to addition acts on non-zero complex numbers by taking power. So if we take an integer n and apply to a non-zero complex number z, we output the nth power of z. This is well defined because z is non-zero, so we have negative powers, and it is easy to see that this is an action. Now let us give an alternative definition of an action. To start with, let us observe that an action of a group G on a set X defines a homomorphism, which we denote by phi, from G to the symmetric group Sx. Proof. If A is an element in G, we define phi of A as follows. Phi of A applied to X is equal to the output when we act by A on X. Then, of course, phi of A is a map from X to X. Moreover, we will now check that phi of A after phi of B is equal to phi of AB. Indeed, phi of A after phi of B applied to X is by definition A acting on B acting on X. By the axiom, this is the same as AB acting on X, and this is equal to phi of AB applied to X. So in particular, phi of A after phi of A inverse is equal to phi of the identity, which is the identity on X. And so each phi of A is bijective with inverse phi of A inverse. So indeed phi is a map from the group G to the symmetric group on X, and because of this line, this map is a group homomorphism, because phi of A after phi of B is equal to phi of AB. So it's a group homomorphism. So each action of a group on a set defines a homomorphism from this group to the symmetric group on that set. Conversely, given a group homomorphism phi from G to Sx, we can define an action of G on X via the following formula. A acts on X. By definition, this is phi of A applied to X. Proof. Let's check the action axioms. The identity acting on X is by definition phi of the identity applied to X. Phi of the identity is the identity map, so it will give us X. Also, if we act by A on the outcome of B acting on X, this is by this definition phi of A applied to phi of B of X. So by definition, this is phi of A after phi of B applied to X. Since phi is a homomorphism, this is phi of AB applied to X. And then it is AB acted on X. And this completes our proof. So this means that the datum of an action of a group on a set is equivalent to a group homomorphism from this group to the symmetric group on that set. In other words, an action of a group on a set realizes each element of our group as a bijective transformation of our set, and this realization is such that the multiplication in the group is realized as composition of transformations. Now let us talk about invariant subsets. Let G be a group which acts on some set X. Definition: a subset Y of X is called G-invariant, or simply invariant, provided that A applied to X belongs to Y for any element A in G and for any element X in our subset Y. For example, for any action of G on the set X, the whole set X is an invariant subset. Example 2, for any action of G on any set X, the empty set is an invariant subset. Example 3, for the natural action of GLV on V, the zero element of V is an invariant subset. This is because GLV consists of linear transformations of V, and any linear transformation fixes this zero element of V. Example 4, for the natural action of Sx on X, the only invariant subsets are the whole set X and the empty set. This is because if we have two elements in X, we can always find a bijection which transforms the first element to the second element. And because of the last example, let us define the notion of a transitive action. So let G be a group which acts on some set X. Definition: this action is called transitive, provided that for any elements X and Y in X, there is an element A in G such that A applied to X gives us Y. Proposition: an action of G on X is transitive if and only if the only invariant subsets of X are X itself and the empty set. Proof: let us assume that the action of G on X is transitive. Let Y be a non-empty invariant subset. Take some element Y in this subset and some element X in the complement. Great, because of the transitivity, there should be A in G which maps Y to X. So if we apply A to Y, we get X. But of course this contradicts the G invariance of the set Y, and consequently such little x in the complement cannot exist. So the complement is empty, which means that Y is equal to X. Now let us prove the converse. So assume that X is a non-empty set and G acts on X such that the only invariant subsets are X and the empty set. Let X and Y be two elements in X. So if they are equal, then of course we can apply the identity to X and get Y. So that's easy. If they are different, let us consider the set which consists of all element A times X, where A is an element in G. So if we have an element B in G and we apply B to A applied to X, by the axiom of the action, this is equal to AB applied to X. So this set is G-invariant. So it's a non-empty G-invariant subset, so it must coincide with X due to our assumption. But then this means that Y belongs to this set, and this means that the action is transitive. So this completes our proof. Here are some examples. Example 1, this we already discussed. The natural action of the symmetric group Sx on X is transitive. Example 2, the natural action of GLV on V is not transitive unless V is equal to the zero vector space. And this is because we have already discussed that the zero subset is an invariant subset. It's a non-empty subset of V, and it is invariant under the action. Example 3. The action of G on G by left multiplication is transitive. And this is because for any pair of elements x and y in G, if we multiply x on the left with yx inverse, we get y. So, by definition, this is a transitive action. At the same time, the action of G on G by conjugation is not transitive, because conjugation fixes the identity element in G. So the identity is an invariant subset. So the conjugation is transitive if and only if the group G consists only of the identity element. Now let us talk about orbits. Let G be a group acting on a set X. Definition: for M in X, the set OM, which consists of all elements A dot M, where A is an element in G, is called the orbit of M in X. So we saw this set in one of the previous proofs. And in that proof we actually showed that this set is G invariant. So the orbit of any element is an invariant subset of the underlying set. Another remark: an action of G on X is transitive by definition if and only if there is only one orbit. So for any element M in X, the orbit of M coincides with X. Here's an example. For the natural action of GLV on V, the orbit of 0 consists of the element 0. So we know that all linear transformations fix the 0 element. Example 2. For the natural action of GLV on V, for any non-zero element little v, the orbit of the little v coincides with the set of all non-zero elements in V. So any non-zero element can be sent to any other non-zero element by an invertible linear map on a vector space. Now let us discuss some properties of orbits. So let G be a group acting on a set X. Proposition: for two elements M and N in X, we either have that the orbit of N is equal to the orbit of M, or these two orbits are disjoint, so the intersection is empty. So in particular, the whole set X decomposes as a disjoint union of orbits. Proof: assumes that we have some element T in the intersection of ON and OM. This means that we can write T as some A applied to M or some B applied to N, so A and B are elements in G. If we apply A inverse to this equality, we get that M, which is equal to E dot M, and E is A inverse A, and now we can move the brackets to get A inverse applied to A applied to M. Now A applied to M is the same as B applied to M, and now we move brackets again and we get A inverse B applied to N. So we just proved that M belongs to the orbit of N, because M is equal to something applied to N. And then, of course, the orbit of M is a subset of the orbit of N. But because of the symmetry of the situation, we also have the converse inclusion, and so these orbits are equal. So if two orbits have a common element, they must coincide. Here is a special case. We can compare this to something which we have already seen in this course. So let G be a group and H a subgroup of G. Then the subgroup H acts on G by left multiplication. So H applied to G gives us HG. And the orbits of this action are exactly the sets of the form the whole subgroup times the element G. And this is exactly a right H coset. So we have an action of H on G by left multiplication, and the orbits are the right H cosets. So our proposition generalizes the fact, which we have already seen, that different right cosets are either disjoint or coincide. Also, one can note that H acts on G by right multiplication, but now we should take the multiplication with the inverse of H. And then the orbits of this action will be exactly the left cosets. So we can also obtain left cosets by a similar construction. And of course we also have the conjugation action of H on G where an element little g is sent to HGH inverse, where H is an element in H. And if H is equal to G, then the corresponding orbits are called the conjugacy classes. Now let us talk about stabilizers. Let G be a group acting on a set X. For an element M in X, consider the set St sub G of M, which consists of all elements A in G, such that A applied to M gives us M. So this set is called the stabilizer of M in G. It consists of all elements of G which stabilize the element M. Proposition: the stabilizer is a subgroup of G. Proof: first of all, if we applied identity to M, we get M. So identity belongs to the stabilizer. Next, if A times M is M and B times M is M, then A times B times M is equal to A times M is equal to M. So if A is in the stabilizer and B is in the stabilizer, then AB is in the stabilizer. So stabilizer is closed with respect to multiplication. Finally, if AM is M, applying A inverse, we get A inverse M is equal to A inverse applied to A times M, which is, we move the brackets, A inverse A gives us the identity, and we get M. So if A is in the stabilizer, then A inverse is also in the stabilizer. So stabilizer is closed with respect to taking inverses. And this implies that the stabilizer is a subgroup of G. Here are some examples. For the natural action of GLV on V, the stabilizer of 0 is the whole group GLV, because all linear transformations stabilize 0. More generally, example 2, if G acts on X trivially, which means that any element of G applied to any element M in X gives us M back, then the stabilizer of any element in G is the whole of G. That's by definition. Example 3, if G acts on G by left multiplication, then for any element M in G, the stabilizer of it is trivial, just consists of the identity. Indeed, if A times M is equal to M, we can multiply this with M inverse on the right to get A is equal to E. And that explains the example. Example 4, for the natural action of Sx on X, and for any element M in X, the stabilizer of M in G in Sx is isomorphic to the symmetric group on X minus M. So if we have a bijection from X to X which fixes M, then F restricts to a bijection from X minus M to X minus M. Vice versa, if we have a bijection G on X minus M, we can extend it to a bijection on X by defining that G of M is equal to M. So this explains this example. Now let us discuss two important facts about stabilizers and orbits. So first is the following theorem. Let G be a group acting on a set X. Let M be an element in X and N an element in the orbit of M. Let A be an element in G such that N is equal to A applied to M. So this exists because N belongs to the orbit of M, so by definition. Then the stabilizer in G of the element N is equal to A times the stabilizer in G of the element M times A inverse. In particular, the stabilizers of N and M in G are isomorphic. So here we say that they are conjugate, so they are isomorphic. Proof. Let B be an element which stabilizes M. Then, if we apply ABA inverse to N, we can write it as A applied to B applied to A inverse of N. A inverse of N is M, B of M is M, and A of M is N. So this means that ABA inverse belongs to the stabilizer of N. And of course, by the symmetry of the situation, if C is an element in the stabilizer of N, then A inverse CA belongs to the stabilizer of M. But this means that we have two maps between the stabilizer of N and the stabilizer of M. One sends B to AB A inverse, and another one sends C to A inverse CA, and these two maps are mutually inverse bijections. And since we know that conjugation is an inner automorphism of the group, we get all claims of our theorem. And here is another theorem. Let G be a group acting on a set X. Then, for any element M in X, the map, which takes the coset A times stabilizer in G of M and maps it to A applied to M, so this map induces a bijection between the left cosets of G modulo the stabilizer of M and the orbit of M. In particular, if G is finite, then the cardinality of the orbit is equal to the cardinality of G divided by the cardinality of the stabilizer of the point in this orbit. Proof. If B belongs to the stabilizer, then applying A to B applied to M, so B applied to M is M, so we will get A applied to M. So which means that this map is well defined. It doesn't depend on the choice of the element in this coset. And of course, this map, coset goes to an element, this is surjective by the definition of the orbit. The orbit consists of all elements as on the right-hand side. So we have a surjective map from cosets to orbits. Let's prove that it is also injective. So assume that A times M is equal to B times M. If we multiply with B inverse, we get B inverse A times M is equal to B inverse B times M, which is the identity applied to M, which is M. And this means that B inverse A belongs to the stabilizer of M. So if AM is equal to BM, then B inverse A belongs to the stabilizer of M. And then, of course, A is equal to B times B inverse A. So our map is indeed injective, and so it is also bijective. And now the formula about the cardinalities follows directly from Lagrange's theorem. Here's an example. Consider S3 acting naturally on the set 1 to 3. So the group S3 consists of 6 elements: the identity, the transposition of 1 and 2, the transposition of 2 and 3, the transposition of 1 and 3, the cycle which sends 1 to 2, 2 to 3, and 3 to 1, and the cycle which sends 1 to 3, 3 to 2, and 2 to 1. So if we take as element M in our set the element 1, then out of this element there are only 2 permutations which stabilize 1. It's the identity and the transposition of 2 and 3. So the orbit of 1 consists of all elements. We can send 1 by a bijection to 1, 2, or 3. And so we see that the orbit has 3 elements, and 3 is equal to 6 divided by 2. 6 is the cardinality of the group, and 2 is the cardinality of the stabilizer. So that's about the last theorem. And also, it is easy to see that the stabilizer of 2 consists of the identity and transposition 1, 3, and the stabilizer of 3 consists of the identity and the transposition 1, 2. And it's now easy to check that the stabilizer of 3 is equal to 1, 3 times the stabilizer of 1 times 1, 3. So here 1, 3 is an element which swaps 1 and 3, and this element has order 2, so the inverse equals to this element. So that's an illustration of the first theorem. Here's a consequence from this corollary. If G is a finite group and X a conjugacy class in G, then the cardinality of X divides the cardinality of G. Proof. G acts on itself by conjugation. So if you take an element M in X, then by definition of the conjugacy class, X is equal to the orbit of M. And so the cardinality of X by the previous theorem is equal to the cardinality of G divided by the cardinality of the stabilizer of M. And so the cardinality of X divides the cardinality of G. So for example, if you look at S3, in S3 we have 3 conjugacy classes: the identity, the conjugacy class consisting of 3 transpositions, and the conjugacy class consisting of 2 3-cycles. So the cardinalities are 1, 3, and 2, and they all divide 6. Here are some problems and questions at the end. Problem question 1. What is the role of the axiom E dot x is equal to x in the definition of an action? So what happens if this axiom is removed from the definition? What happens then? Problem question 2. Prove with all details that for the natural action of GLV on V, the orbit of any non-zero element coincides with all non-zero elements. Problem question 3. Prove with all details that the fact that some element m belongs to the orbit of n implies that the orbit of m belongs to the orbit of n. Problem question 4. Check with all details that any subgroup H of a group G acts on G by right multiplication with H inverse. And problem question 5. What can we say about a group G if we know that the conjugation action of G on itself is transitive? Thank you very much and see you next time.